Good morning, students. So in our last class, I studied about logic and propositional calculus, propositional logic, natural deduction system, and we looked at some of the examples of theorems, how to prove, how to derive or deduce an expression from the given formula. Today, we will look at axiomatic system. Axiomatic system is the second kind of method that we looked at yesterday. Look at this, there are 4 different kinds of methods that perform these proofs and deductions. First one was natural deduction system. Second is axiomatic system. Third one, a semantic tableau method. And fourth one is a refutation method. First 2 methods are direct methods and they deduce or prove by using forward chaining. In last 2 methods, third and fourth methods are indirect methods and they prove through backward chaining. So yesterday we discussed about natural deduction system. There are 10 rules in this. You can introduce logical operators like and, or, implies, equivalence. You can eliminate also based on the rule and the description given in the table. And also we looked at how to deduce a formula from the given expression. Axiomatic system is also a deduction system. It is a very simple system having only 3 axioms and 1 rule. However, its power is as equal as that of propositional logic or natural deduction system. And one important point to remember here is that axiomatic systems, all the formulas or expressions are expressed in terms of not and implies. You cannot use and or equivalence logical operators in axiomatic system. If the formula given contains and or equivalence logical connectives, we need to represent them using only not and implies by using this laws, equivalence laws, where A and B is equivalent to not of not A or not B, which is equivalent to not of A implies not B. So if A and B is given, you have to convert it into this form, not A implies not B. If the given statement is A or B, then you have to write not A implies B. To prove or to deduce in axiomatic system. So the 3 axioms are these. alpha implies beta implies alpha. This is axiom 1. Axiom 2, alpha implies beta implies gamma, and the whole formula implies alpha implies beta, which in turn implies alpha implies gamma. And axiom 3, in this you have uh, not alpha implies not beta. Further implied 2 beta implies alpha. And the deduction rule is called as Modus Ponens rule. This Modus Ponens rule is very, very important. You all have to remember this. This occurs in natural deduction system also. There are 10 rules in NDS. In this, eliminating implies. Look at this. This rule is called as Modus Ponens rule. So in this, what happens is, if A1 implies A and there is A1, then you can write just A. That is Modus Ponens rule. So let us look at an example. You have this hypothesis alpha implies beta and alpha. So the result is the consequent, which is beta. Beta here is called as a consequent. So if you find this type of formula, then you can just write beta in the result. If you have any doubt, you can raise your hand and ask me. Look at this example. In this, there is a formula given, A implies C, which is a deductive consequence of A implies B, comma B implies C. So this can be written in this form. This is a symbol to denote deduce. So A imply B, comma B implies C, deduce A implies C. How can we prove this? To prove this, you need to start with the given theorem. The given theorem is this: A implies B, comma B implies C, deduce A implies C. And if you observe, all the tables have 3 columns. First one is the description, in which you mention whether it is a hypothesis, it is an axiom, or is it a rule that you are applying on the line number. Here the third column specifies the line number. Whenever you apply a rule, in this first column you specify the line number on which you are applying a particular rule. That rule also you mention, and line number you mention. And in the middle column contains the formula and how it is deduced from the given theorem to the deductive formula. So when you start this, A implies B and B implies C. So hypothesis 1, you are considering A implies B is true, and means you are splitting it. You are breaking it down into 2 subformulas. So A implies B and B implies C, and you are giving them numbers as 1 and 2. And then you are applying in axiom 1 on this. How you are applying in axiom 1? What happens? Alpha implies, within parentheses you have beta implies alpha. So here you are considering beta B implies C, implies here this A, this is like A in alpha in axiom, and this is like beta in axiom, and beta implies alpha. Next you are applying Modus Ponens rule on line number 2 and 3. What is line number 2? This B implies C. What is line number 3? That axiom 1. When you look at this, you find that B implies C, B implies C. they both are common. So what modus ponens rules say, when you have alpha implies beta is one formula, and you have just the alpha as one formula, then the output, what you can write, only the beta, you just omit alpha. So when you apply modus ponens on line number 2 and 3, then you get only the beta part, the consequent part, which is A implies B implies C. This is line number 4. Next, on this, again you are implying, you are applying axiom 2. Axiom 2, if you look at, there are three variables in axiom 2. Alpha implies within parenthesis, beta implies gamma, and then you have like a distributive property here. Alpha implies beta, which further implies alpha implies gamma. So after you get this, which is line number 5, you again apply modus ponens rule. Modus ponens rule, when you apply on line number 4 and 5. In line number 4, you find A implies within parenthesis B implies C. And then in line number 5, so this is like alpha, and this is alpha implies beta. So in modus ponens rule, what you do? You just eliminate alpha part. You write only the beta part, which is the consequent. So after application of modus ponens, you get only alpha, A implies B, and which in turn implies A implies C. So this is what line number 6. Further, you are applying modus ponens on line number uh, 1 and 6. Line number 1 has A implies B, and line number 6 has A implies B and A implies C. So it is like, this is like alpha, and this is like alpha implies beta. So what happens again, according to modus ponens rule, you just eliminate alpha and just put the beta in the result. You got the beta, which is A implies C. And what was our goal? Our goal was to deduce A implies C from this formula. And we could successfully do it by using these axioms and modus ponens rule. So here it requires lot of creativity and lot of knowledge about which axiom to apply at which level. So this is about axiomatic um, system. In again, another example of this axiomatic system is, you have to prove deduce. You have to deduce. If you look at this example, here you are writing this symbol for deduction before the actual formula. That is also possible because of deduction theorem. Here in the deduction theorem says that if alpha implies beta is proved from a sigma, then what you can write is, you can write deduction of alpha implies beta. So from this theorem, you can write this formula like not A deduce A implies B. You can write this one in this form, wherein you just put the symbol for deduction before the formula. So that is our theorem. The theorem is that not A deduce A implies B. We have to prove this. To prove this, what we are doing, we are considering this not A to be hypothesis, to be the true statement, and then you are applying here axiom 1, and then you are putting modus ponens on line number 1 and 2. When you put on line number 1 and 2, because this not A, these two are like alpha part, When you have a separate alpha and alpha implies beta, then you omit alpha and you just write the beta. So beta part is this, not B implies not A, which you are putting as a result of application of modus ponens on line number 1 and 2. The next step is we are applying here axiom 3 on this result which we got after applying of modus ponens. And then when we got this through axiom 3, again modus ponens rule is applied on line number 3 and 4, and then not B implies not A. This is like alpha part, it has been vanished, and then you got A implies B. So it is proved that we can deduce A implies B when not A is given as a formula. This axiomatic system, although looks to be simple, but it is very powerful and it can do any type of deduction and proof. Um, the main problem of NDS, that is natural deduction system, and AS, that is axiomatic system, is that they require a lot of guesswork because you need to ensure that you are putting the right kind of rule to deduce the required formula given, and as it evolves this derivation process, eventually the result what you get should be same as whatever was asked in the theorem. So that requires a lot of creativity, and it becomes difficult for a machine to do that type of task. So these another two methods called semantic tableau and resolution refutation methods were developed. These two methods work uh, not from a forward direction, rather from the backward direction. So that way they prove that whether we can deduce a particular formula or not. Semantic tabuli, this is a uh, set of rules that are expressed in the form of a tree. You have a tree in which you can have two branches or you can have one branch, and the formula will be placed as the root of the tree, and from that root you can split it up into sub formulas, and these rules are given in table 4.11. You have rule number 1. If you look at rule number 1, it is alpha and beta is true if both alpha and beta are true. You know about this. But how can you write in the form of a semantic tableau rule? You put this formula alpha and beta, and then what you do is you break it up into alpha and beta as the branches of the root. So you likewise you do for rule number 2. In rule number 2 you have another formula. For different kinds of formulas you have different rules and different ways of putting in the form of a tree. So not A and B, you can write this as not A as one successor and not B as another successor. So you got left and right two children, both are derived from the expression or the formula which is not within parenthesis A and B. Likewise, you have 9 rules. You can go through the rules. Let us look at an example how we can construct a semantic tableau for a formula. The formula given is A and not B, and within parenthesis not B implies C. In this, if you look at this formula, it has two subformulas. So we have to look for the rule, which rule to apply from the rules given for semantic tableau. Again, you are putting everything in the form of a table. You have three columns: description, formula, and line number. In the description, you are starting with a given formula, and then you are applying rule number 1. Rule number 1, rule number 4, and rule number 7, they are single branch rules. So you should prefer to apply these rules. If you look at rule number 1, like it is single branch loop, and rule number 4 is also like that, and rule number 7 is also like that. So if you apply rule number 1 on A, alpha, and beta, so if you consider this part, the first subformula as alpha and the second subformula as beta, then you can express this formula in this manner, where the root formula has been um, put up in the form of branches, where you have alpha as the first branch and then you have second as beta. So you are applying rule number 1 on line number 1. This line number 1, this is rule number 1 on line number 1. So you got another for two more lines you got after application of this rule, and then you are applying rule number 1 on line number 2. Line number 2 is A and not B. And you, how you are applying rule number 1? You write A and not B. A and not B. It is like this is alpha and this is beta. And then on line number 3, on this line number 3, you are applying rule number 6. Rule number 6 states that when we have alpha implies beta is true, then not alpha or beta is also true. So you can write alpha implies beta as one side left not alpha, and to the right you can write beta. So that is expressed here. On line number 3, you can find that you have not B implies C. So how you are writing it as because not B is like alpha, so one more not you have to introduce. So not B and this C. When you apply rule number 3 on line number 6, this, because these two are these two are complementary. Actually, this is like B only. This side, this B, this is not B and this is B. This not B becomes B, and this not B and B, they are eliminated because they are complementary in nature. One is B and one is not B, so they get cancelled. So this path is closed because of B and not B, whereas this path uh, of C is open. What does that mean? We will look at here. In another example. So okay. In this example, your formula is this, which is denoted by line number 1, and then you are applying rule number you are applying rule number 1 on this line number 1. Rule number one on this line number one, to get these subformulas separated. So you got not A or B, and you got C implies B, and you got A or C as separate subformulas. Then you are applying on line number two, rule number four. Line number two is this, and rule number four you are applying as, what is rule number four? Rule number four says if you have not A or B, if this formula is true, um, if this formula will be true if both not alpha and not beta are true. When both these literals are true, then the entire formula is true, and hence you write this formula as not alpha uh, and not beta. So that you are writing here. Here you are writing as not alpha and not beta from this line number 2. Next you are applying rule number 3 on line number 4. Line number 4 is this, A or C. This A or C from rule 3 can be written as A and C as left and right children. So further, if you um, apply this side, this path will be closed because you have here A and not A. A and not A will get sort of cancelled, and then this path gets closed. Whereas in this path, if you see, you are applying on formula rule 6 on line number 3. Line number 3 is C implies B. C implies B can be written as not C as left child and B as the right child. So when you write like this, you get again complementary symbols. So you get here not C and C. So again they both get cancelled, and then this path is also closed. Further you cannot apply any rule on this. And then this also, because it's parent's parent, here not B and this is B. Again both get cancelled. So this path is also closed. Okay, next example is show that a set S is equals to not A or B, comma B implies C, comma A or C is consistent. So I just give you 5 minutes time. Please go through this and ask me if you have any doubt. Please go through that example. So our meeting will end in 10 minutes. So I urge you all to please, you all have the soft copy of the textbook. Go through this example. Let me give you um, a basics. Let me introduce you to resolution refutation. In this method, what happened? This is the last method. It also follows the backward chaining approach, and in this the formulas are expressed in the form of clauses, and you have certain rules to convert the formula into a set of clauses. As you know, in propositional logic there are two normal forms, disjunctive normal form and conjunctive normal form, and these normal forms are constructed using three logical connectives, which are not, and, or. In DNF, disjunctive normal form, it is internally it is connected by and the terms will be connected by or. Whereas in CNF, which is conjunctive normal forms, you have the other way. And to convert a formula to its CNF, that is a conjunctive normal form, you need to follow these equivalence laws, and then certain steps you have to take to convert a formula into CNF. If you look at this formula, convert this formula into its equivalent CNF. For that purpose, you need to refer to these equivalence laws. Equivalence laws given are, you know this, and this is De Morgan's law, and this is distributive law, and this is you have to eliminate implies and equivalence, because in CNF there is no implies and there is no equivalence operator. It has not and or. So for that, if you look at here, what you are doing is you are expressing this formula not A implies B as, you see here, A implies B can be expressed as not A or B. So you are writing here A, not A implies B as not A, that not is connected to A, so that will remain, and then this not comes from this equivalence rule, and or B. And because here you need not do any transformation, because it itself is in CNF. And then this will become not means not A is A or B, and C and not A. This C and not A can be expressed as this. These nots you can eliminate. If you remember, there we have some rules where you can um, introduce and operator, or you can eliminate and operator, you can introduce or operator, you can eliminate or operator. So from those rules, here we are eliminating and. So you can write this as A or B, comma C, comma not A. This is set of clauses. Each one is a clause, and it is written by following the equivalence laws. So here what you have to do is, in this example, you have to find a resolvent of the clauses in the set. Uh, you have been given a set of formulas or clauses. Here we call them as clauses, and then you need to find the resolvent of that clause. You start with this A or B and uh, not A or D. Again, as you know, here you have A and here you have complement of A. So that both goes away and you get only B or D. From these two, when you combine these two clauses, you get this clause, A, B or D. And then when you combine B or D clause with C or not B clause. Again, because you have B and not B, that gets eliminated, and then you will get C or D. So this C or D, because there is no other clause in this to combine with, because all the clauses have been done, the C or D is called as a resolvent of this set. And likewise, you can do for this A or B. This is given using resolution refutation principle. Show that C or D is a logical consequence of this set which contains three clauses A or B, not A or D, C or not B. What happened here is this problem. In this problem, given a set of clauses, you are trying to find the resolvent, whereas in this you have to prove that C or D is a resolvent or a logical consequence of this. In that example, C or D was not given. You need to derive it. Whereas in this, C or D is given, and you need to prove that in fact C or D is a resolvent of this. So how can we prove? We can prove again by combining. You have to choose the two clauses such that you get complementary literals. When you get complementary literals, you just cancel them, and then if you get uh, cross which state that it is over, means no further clause is there. So it is like we conclude that C or D is in fact a logical consequence by applying all these clauses together, and then cancelling the contradictory ones, and then ending it with cross. So um, this is about the resolution of classes, how you can perform resolution by contradiction. Still 2 minutes are left for our class to complete. If you are having any doubt, you please put in the chat so that I can clarify your doubts. Okay, students, then I will end the meeting for today. Again, tomorrow we'll continue with the next topic. Please go through the text to try to understand. And I'm planning to conduct one objective type exam through Google Forms on Saturday. All of you please prepare. Whatever topics we are covering, I will create some objective type questions. You need to fill the answers in the Google form and submit. Okay, students, bye. Have a good day.